Imagine a world, frozen in ice, yet hiding beneath its surface an ocean, Europa, one of Jupiter's enigmatic moons. This subsurface ocean hints at a habitat that could support life forms, potentially reminiscent of the earliest organisms on Earth. As scientists delve deeper into astrobiological research, Europa emerges as a tantalizing focal point for the quest to discover life beyond our planet. But what if chemical reactions combined with energy from the ocean currents beneath Europa's icy exterior could weave together complex food webs? This intricate web suggests a thriving biosphere could exist, one that is crucial for sustaining diverse forms of life. Could this complex ecosystem be waiting to be uncovered, bursting with life? As we peer into the cosmos, the discovery of hydrothermal vents on celestial bodies similar to Europa teases an exhilarating possibility. Might life exist in parallel environments, nourished by heat and chemical-rich waters? This tantalizing notion invites us to explore Europa's potential life-sustaining conditions further. Yet, the landscape of Io, another of Jupiter's moons, presents an entirely different narrative. Here, volcanic activity dramatically alters the surface temperature, with pockets of heat reaching levels that could allow liquid water to emerge. What secrets lie hidden in these thermal gradients that suggest the moon's complex geological environment? Intriguingly, the presence of sulfur dioxide and hydrogen sulfide opens up a new realm of possibilities. Could these solvents exist in places on Io that might support life? Even in the absence of water, life could theoretically find a foothold under the right conditions. The question remains, what forms could life take here? Jupiter's formidable magnetic field and the gravitational flexing it imposes on Io stir the pot of geological activity. This dynamic interplay creates an environment that beckons life forms uniquely adapted to survive in its extreme conditions. What strategies must these organisms employ to thrive amidst such turmoil? However, the emergence of life on Io is fraught with challenges. The moon's stark aridity and rapidly shifting environment raise pressing questions. How long would life need to endure before it could flourish? What barriers must it overcome to adapt to such an unforgiving realm? Research unveils a tantalizing hypothesis. Life could have emerged in ephemeral sulfur dioxide lakes, offering a unique biochemical arena unlike our familiar water-based systems. Could these transient environments have been the cradle for early cellular life, waiting to be discovered? Yet, survival would demand incredible resilience. Potential life forms on Io would face relentless radiation from Jupiter's magnetosphere, presenting further complications. How might these organisms evolve to withstand such an extreme setting, and what might they look like? Microbial life on Io could be characterized by rapid reproduction and small size, adapting swiftly to its volatile environment. This rapid adaptation is the lifeline for survival. Could these diminutive organisms hold the key to our understanding of life beyond Earth? Yet, the sensory capabilities of life on Io would diverge drastically from our earthly experience. Instead of vision or hearing, they might rely on touch and chemical perception, showcasing a starkly different approach to survival in their hostile world. What adaptations could emerge in such life forms? The relentless geological activity on Io, marked by explosive volcanic eruptions, creates fleeting habitats that could support life, albeit temporarily. These transient environments offer unique chemical landscapes, rich with opportunities for potential organisms. What mysteries lie within these ephemeral havens? Shifting our focus to Venus, the last major eruption likely altered its atmospheric dynamics around 500 to 700 million years ago, pushing it into an inhospitable state. What once may have been a cradle for life now seems incredibly hostile. How did Venus fall from grace? Initially, conditions on Venus appeared promising, with liquid water and a stable atmosphere echoing the early environments of Earth and Mars. With such potential, what went wrong? How did this once breathable world become one of the most extreme environments in our solar system? As temperatures spiked and water evaporated, life forms would have faced insurmountable challenges, adapting to severe heat and acidity. The harsh conditions spelled doom for many species. Can we imagine what life might have looked like before this cataclysmic transformation? Once akin to Earth, Venus's evolution showcases the profound impact that proximity to the Sun can have on planetary development. How does this transformation inform our understanding of habitability in the cosmos? The contrasting atmospheric compositions of Venus and Mars reveal the myriad conditions that can influence a planet's ability to harbor life. Could such diversity offer clues into where life may thrive beyond Earth? Mars, Earth's smaller sibling, bears the scars of significant geological changes, revealing evidence of ancient water flow. Could these signs point to a past where life might have flourished, waiting to be unraveled by future exploration? Once a humid and warm planet teeming with liquid water, Mars has undergone a chilling transformation, losing its atmosphere and plunging into the cold. How did this drastic shift impact its geological landscape and its potential for life? Frequent meteorite impacts and volcanic eruptions have sculpted Mars' surface, giving rise to features like Olympus Mons. These geological processes are pivotal for piecing together Mars' evolutionary tale. What stories do these formations hold? Could the evolution of autotrophic life on Mars have been feasible due to water's presence and favorable conditions? Imagine nurturing life forms that could lay the groundwork for more complex organisms. What might these early pioneers have looked like? Motility may have granted early Martian organisms the edge in food acquisition and survival, echoing Earth's evolutionary journey. How crucial is this trait for thriving in a world of fluctuating environments? The transition from unicellular to multicellular life on Mars seems plausible, suggesting a remarkable adaptability to aquatic habitats before venturing onto land. Could this progression mirror the evolutionary steps taken on our home planet? As Mars underwent dramatic climatic shifts, the pressure to survive likely forced life underground, where moisture and resources might have lingered. What kind of unique subterranean ecosystems could have thrived in these hidden realms? Freshwater environments could have played a significant role in the emergence and diversification of early life on Mars, even if their existence was fleeting compared to the oceans. What rapid adaptations might have occurred in these simpler life forms? Remarkably, cave ecosystems formed by lava tubes could provide refuge for Martian life. In these protective habitats, organisms may not only survive but potentially thrive despite harrowing surface conditions. What kind of biodiversity could exist in these hidden sanctuaries? Research into Earth's extreme environments, such as the unforgiving Atacama Desert and the Antarctic dry valleys, sparks curiosity about the resilience of life on Mars. How might these earthly analogs illuminate our understanding of potential Martian life forms? Yet, the ability of life to navigate and flourish under Martian conditions may have faced limitations, curtailing biodiversity. Could the advantages provided by aquatic habitats have made a difference for early life forms seeking to thrive? Sensory systems in Martian organisms were likely elementary, shaping their interactions with the environment. How might the slow evolution of complex sensory systems have constrained their adaptations? Evidence surfaces suggesting that microbial life might have once thrived on Mars, as indicated by studies examining Martian rocks. Yet the debate rages on among scientists. Did life ever exist here? And what does that mean for our understanding of life in the universe? Zooming back to Europa, the chaotic movement of ice plates reveals fissures and distinct geometric formations, painting a picture of dynamic geological activity beneath. What's driving this movement under the frozen surface, influenced by the immense gravitational forces of Jupiter? Scientists propose that Europa's subsurface ocean is nourished by tidal heating and radioactive decay, a lifeline allowing for liquid water to persist beneath the icy mantle. How vital is this heat for sustaining potential life in such a frigid realm? The presence of organic chemistry precursors, such as methane and hydrogen sulfide in Europa's environment, invites a provocative inquiry. Could these compounds shield the potential for life? Understanding their role may hold the key to thriving amidst extreme conditions. At the very foundation of an ecosystem, producers harness abiotic resources for energy, with phototrophic organisms relying on the scant sunlight filtered through icy layers. How does this restricted growth inform the adaptation strategies that could evolve in such environments? Microbial life forms, particularly radiolytic chemotrophs, may find their niche in these harsh conditions, thriving through chemical reactions like hydrogen reduction. Yet their slow growth, a consequence of limited resources, poses a question of viability. How well can such organisms adapt? Classifying organisms as lithotrophs or methanogens reveals the diverse energy sources these life forms might exploit in extreme settings. Each group plays a distinct role in the ecosystem's energy flow, hinting at a rich tapestry of life potentially lingering beneath the surface. Across different models of ecosystems on Europa, the influence of energy sources profoundly shapes the potential for diverse life forms lurking in its ocean. The significance of radiolytic oxygen production looms in this research, inviting us to ponder what life could really be like. Could organisms the size of tadpoles thrive in Europa's waters, their distribution impacting overall population viability? These findings suggest a complex interplay of ecosystem dynamics, revealing the fragile nature of life in this alien ocean. Despite the extreme cold and radiation challenges on Europa, microbial life may yet flourish in sheltered niches beneath the ice. This extraordinary adaptability hints at the potential for unique biological communities awaiting discovery. The subsurface ocean of Europa proves vital for supporting life, harboring liquid water and a variety of energy sources. The sheer chemical richness of this environment remains a tantalizing area of ongoing research, leaving us to speculate. What life could exist here? Potential life forms on Europa could exhibit surprising characteristics, showcasing low mobility and rudimentary sensory systems that starkly contrast with terrestrial life. What adaptations might arise from the harsh conditions, redefining our understanding of life itself? Finally, as we broaden our horizons to Enceladus, another intriguing moon sharing similarities with Europa, we find the possibility of multiple celestial bodies harboring life. What other hidden wonders lie within our solar system, waiting for discovery? Intense thermal gradients on Io, shaped by Laval flows and frozen sulfur dioxide, contribute to its extreme environment. The question arises, how might these gradients facilitate chemical reactions essential for life? Exploring the unique properties of sulfur dioxide and hydrogen sulfide unveils potential solvents for life on Io. Could these compounds enable biochemical processes to thrive under the most extreme of conditions? Moreover, the influence of Jupiter's powerful magnetic field and its rotation might serve as energy sources, potentially fueling biological processes on Io. What life forms could arise, drawing upon these celestial energies? Liquid sulfur dioxide pools may offer the crucial conditions for early life forms to develop on Io, presenting an enigmatic environment requiring stable atmospheric pressure to prevent evaporation. What else could be hidden in these strange landscapes? The geological upheaval on Io, characterized by lava flows, could intermittently forge habitable environments. Might these processes melt and mix minerals, crafting conditions ripe for the emergence of life? Yet, the specter of radiation on Io looms large, imposing significant hurdles for any potential life forms. What unique adaptations would organisms need to survive and thrive in such high radiation environments? Sensory adaptations become imperative for potential life on Io, with organisms possibly relying on touch and olfaction instead of vision to navigate their harsh world. What might these adaptations reveal about their existence? The relentless volcanic activity on Io gives rise to fleeting habitats that, if temporary, might still support life. As these habitats form from ice melting due to volcanic hotspots, we ponder, could such moments allow life to flourish? In the end, life on Io might challenge our definitions of biological systems. What unique chemical structures and metabolic processes could emerge in organisms uniquely adapted to their extreme surroundings?